Welcome to this lecture in the ongoing series of lectures in real analysis. We are starting a new module. This will be about integration. So far we have done continuity and differentiation, but now we'll be doing integration. This is again very easy. Everything here is going to be very easy, except for maybe one lemma. Even that is not very hard in my opinion. But the main difficulty in this module will be a bunch of notations and definitions. It will be a whole slew and barrage of them. So, okay, let's start. So what we have is, well, today we'll be defining upper and lower integrals of certain kinds of functions. So here is the setup. So let f be a bounded function. And recall this means that there is some capital M such that fx is less than equal to capital M throughout for each x, and there is some little m such that fx is at least little m for each little x. So basically the function f is sandwiched between two finite values. Okay, so we have such a function, and we will define the upper and lower integral for such a function. So it's a very broad class of functions for which we will be able to define upper and lower integrals. Just boundedness is needed. Okay, so a subdivision of this closed interval is a finite list where n is greater than equal to 1 and a naught is equal to a. These inequalities hold, and an is equal to b. So let me write it in a different line. A naught is equal to a and an equals b. So that is a subdivision of an interval. So this has nothing to do with the above line. Basically, take any closed interval. This is how you define a subdivision of it. In pictures, suppose I have this. This is a and that is b, and we choose some points wherever we like. Dot dot dot. This is, let's say, an minus 1, and the last one is an. Any such thing is a subdivision. The terminology is self-explanatory. Okay. Even this qualifies as a subdivision. So you can have a naught a1 as a subdivision, where of course a naught better be equal to a and a1 better be equal to b. So basically no points in between, only the endpoints. That's also a subdivision, and this is called the trivial subdivision, which I am not writing. Okay. So now let sigma be a subdivision of this interval. We write Li sigma as Li sigma is the length of the ith part. So if this is our subdivision, then L2 would be this length, A2 minus A1, L3 would be that length. So basically the length of the ith part is Li. The norm of sigma is defined as n sigma equals maximum of all these lengths. So the norm is kind of measuring how fine the subdivision is. The smaller the norm, the finer the subdivision. We also define m sub I sigma equals supremum of the value of fx over the ith part Similarly, we define little mi sigma as the infimum of the values of fx over the ith part. And one more thing is omega sub I sigma. This is merely the difference. And this is called the oscillation of f. Over the ith part. So here we are suppressing the dependence on f in this notation. We should technically write it because this depends on the function f. If we take a different function, this will be different. And if there is some confusion that can occur, then we will qualify this with some superscript or subscript. We'll think about that. But for now, I won't write any superscript because there is only one function that we are discussing. Okay, so already a lot of definitions, but now we can define the upper sum and the lower sum. So the upper sum of f for the subdivision sigma is defined as, well, there is this notation, and then again here we should write an f, but I'm suppressing that. And we'll see what is the geometric interpretation of it. That is the upper sum. Let's see, there's a picture here. So, okay, let me transfer this picture. Yeah. Right. So let us interpret this. We have this function. I have drawn a continuous function, but the function doesn't have to be continuous. This is a, and that is b, and this is the subdivision. All these things. And now, if you consider the first term here, meaning I equals 1, that is m1 sigma L1 sigma. What is m1 sigma? M1 sigma is the supremum of f over the first interval. So it is this value, meaning the length of this vertical thing. That is the supremum of f over this. And we multiply that by the length of the first part. So it is this area. The second guy is m2 times L2. M2 is the maximum over this region, which is, or not the maximum, the supremum over this region, which is this much. And similarly, we multiply it by that, so it is that area. But what is m3? M3 is supremum over this much, which is this guy. So it's not necessary like you'll always get supremum in the rightmost thing. Of course, it can come from somewhere in between. Or it may not be even achieved. It's not necessary that the supremum is achieved. Since I've drawn a continuous function, the supremum will always be achieved, but it is possible that there is no point in this interval where the supremum is achieved. That's okay. So it is this area and so on. So basically this thing kind of upper approximates what we would like to call the area under the graph. Our ultimate aim is to define what we mean by the area under the graph, and this is sort of an upper approximation of it. This clearly overestimates that area. Similarly, we define the lower sum. So let me highlight. So the lower sum for the subdivision sigma is defined as you can guess. It's a little s that we use to notate it. Again, there should be a small f, but I'm suppressing that. And this is summation I equals 1 to n. It's little mi sigma li sigma. So that will, I haven't drawn it in the figure, but that will look like this guy and then that guy. And well, maybe this thing. And so on. So you can figure that out. So the lower sum underestimates the what we would like to call the area under the curve. Okay. However, I would like to give a small warning. That the upper and the lower sums are signed areas. So this has to be considered with its sign. Here in my diagram everything is positive, but if this value were below the x-axis, then that should be multiplied with its sign. So that's evident in the algebraic definition, but geometrically one should be mindful of that. All right. So we have defined the upper and the lower sums. Now we can define the upper and the lower integral. So the upper integral of f is defined as, well, the notation is this and the definition is supremum over supremum of all the upper sums where you're using all the subdivisions. Sorry, what have I written? It's the infimum. Sorry about that. So that's the definition of the upper integral. Let us also interpret this geometrically. So here what we are doing is, we are taking the upper sum corresponding to every subdivision and then taking the infimum. So sort of the smallest upper sum that you can get. I shouldn't say smallest because it's an infimum. It may never be achieved for any particular subdivision, but still. So here what you're doing is let's say you take a finer subdivision, then intuitively at least it should be clear that the upper sum will decrease. If you take a finer subdivision, the upper sum corresponding to that subdivision will be at most the upper sum that you get for the original subdivision. So you kind of take finer and finer subdivisions, and you know the finer the subdivision you take, the better will be your approximation for the area under the curve. That is intuitively what's happening. So that's the upper sum, and that's the upper integral, and similarly we define the lower integral. The lower integral of f is defined as The notation is this. So previously we had a bar above, now we have a bar below, which is the supremum of all the lower sums as you vary over all the subdivisions. So it's the kind of the best underestimate for the quote-unquote area under the curve. Kind of the finer you make your subdivision, the better you would approximate the area under the curve. So that's the upper sum, that's the upper integral and the lower integral, and it is not necessary that they are equal. And that's, again, if you just think geometrically, then they would look like equal, but we'll give examples where they may not be equal. Okay, but before we get there, note that this guy, meaning the upper integral, is at most m times b minus a, where what is m? M is the supremum of fx over its domain. So, well, that is very, very clear because each of these guys are smaller than m. So this is less than equal to summation I equals 1 to n m li sigma. M can be pulled out, so what you get is summation li sigma, but that is precisely m times p minus a. So there is an inequality here, right? So we have this is a simple estimate, and similarly we have this. Let me write it differently. Where this guy is infimum of f over its domain. So we have those two things, and it may seem intuitively obvious that this is the case, and that is true, but it is not immediately obvious, and we'll need to do a little bit of work to show that yes, indeed, that is true. But before that, let us at least take one example. So let f be this function. Let me say, okay, fine, no problem. Be defined as fx equals 0 or okay 1 if x is a rational number in this interval, and 0 if x is not a rational number in this interval. So then the upper integral is b minus a, while the lower integral is 0. And let me explain that. I won't be writing the details, but the explanation is very simple. Whatever subdivision you take, the upper sum corresponding to that subdivision is 1, because in the upper sum these quantities will always be 1. You're taking the supremum of f over some non-degenerate interval, meaning it has some interior, and therefore there will be points inside where the function takes the value 1. After all, the rationals are dense. Therefore the upper sum corresponding to any subdivision is b minus a, because all of these are equal to 1. And similarly the lower sum is 0, because all of these will be equal to 0. So the upper integral is b minus a, while the lower integral is 0. And this is an example where the upper and lower integrals disagree. There are many other examples, but for now we'll be content with this. So the rest of the thing is to show that. We now proceed to show that. The lower integral is dominated by the upper integral. Okay, so for that we introduce a little bit of a definition again. Sorry about that. It is refinements. Okay, so let sigma and tau be two subdivisions. Of a comma b, and let's say sigma is your a naught up to a n, and tau is, let me write a little m here, and tau is b naught up to bn. So we say that tau is a refinement of sigma if this happens, which, well, I'll explain, but it should be anyway clear what this is trying to capture. If this happens, and we write sigma, this funny less than tau to denote that tau is a refinement of sigma. So that's a notation. And what is the meaning? Meaning is very simple. Meaning is you have sigma so tau is basically include all the points that sigma had, just introduce some more. That's the notion of refinement. And here is one simple exercise. It's hardly an exercise, but let me state it that way. Suppose sigma is refined by tau, then show that the norm of sigma exceeds or it is at least the norm of tau. Okay. Here is another very simple fact which I will perhaps prove. So if sigma is refined by tau, then S tau, meaning the upper sum corresponding to tau, is at most the upper sum corresponding to sigma. And the lower sum corresponding to, okay, sigma is at most the lower sum corresponding to tau. So it gets flipped. And well, it is very simple. The point is, let me just argue via an example. So suppose sigma were, this is not really a proof because I will be doing it in a very special case, but that idea easily extends to the general case. So here suppose sigma is a naught comma a1, meaning it's just the same as a comma b, the trivial subdivision, and tau is a naught a1, okay, not a naught a1, this is b naught b1 b2. So sigma is just a and b, this is sigma, and tau is, you have a, you have b, and you have some extra guy which we are calling b1. It's a pretty bad notation. But anyway. So what is S sigma? S sigma is just m b minus a, where m is equal to supremum of fx over the entire thing, and S tau equals m1 b1 minus a plus m2 b minus b1, where let me just say what is m1. M1 is the supremum of f over this region, and m2 is the supremum of f over this region. But clearly m1 is at most m, and m2 is also at most m, because m is the supremum over the entire thing. So supremum over a small region, of course, is cannot exceed the supremum over the entire thing. So we have that, which implies, sorry, what have I written? This is b1 minus a, and that is b minus b1, which is that. So we have just used the fact that m1 is at most m and m2 is at most m, and that's it. So you can just kind of inductively prove this. You can assume that tau is formed by adding just one point to sigma and show this inequality, and then after all, tau can be formed out of sigma by adding some finitely many points, so you can just proceed inductively and prove this. Similarly, you can prove that. So this is very easy, and I won't be saying anything more about this. Okay. And now let me also introduce the notion of common refinement. There are two refinements here, sorry. Forget about that. So common refinement is let sigma and tau be two subdivisions. Let's say sigma is a naught up to am, and tau is b naught up to bn. And you can in fact guess the definition. So the common refinement of sigma and tau is the subdivision rho equals c1 or c naught up to c, what should I write, maybe p, such that, well, p is very bad, let me write a capital N, such that the set is the union of the sets corresponding to sigma and tau. So all we are saying is that whatever points were there in the sigma, in the subdivision sigma, and whatever points were there in the subdivision tau, just put all those points and form that subdivision. So once you have a sequence of points, then you can just arrange them in increasing order and get a subdivision, because this of course contains both the endpoints, a naught and am. Now there could be repetitions here. The same point here can repeat here, so that's why we are taking union. In a subdivision, you don't have a repetition. Subdivision is not a set; it's a list. So once you have a set, you can form a list out of it. Okay, so I am sure you understand what I'm trying to say. It's a common refinement. And now here is our next lemma. So let sigma and tau be any two subdivisions. Then the lower sum corresponding to sigma is at most the upper sum corresponding to tau. So no matter what these two subdivisions be, I'm not saying that tau is a refinement of sigma or anything, just any two subdivisions, and we have this. And the reason is very simple. Let rho be the common refinement of sigma and tau. Then of course we have sigma is refined by rho and tau is also refined by rho. So therefore, so first let us look at this. Now we want to have S sigma. S sigma, yeah, if you refine something, then the lower sum will increase. So what we have is S sigma is at most S rho. So I'm using little s. Because of this we have that. I think that thing. So that's one thing, and the other thing will give us that S rho is at most S tau. So in the upper sum the thing flips. If tau is refined by rho, then S rho is at most S tau. In the upper sum things get flipped. So we have that, but we also know this. This is obvious. For a given subdivision, the lower sum is of course at most the upper sum. So we have that, and this implies S sigma is at most S tau. So we have that. And now we can prove our fact that the lower sum is at most the upper sum. What am I saying? The lower integral is at most the upper integral. I always get confused between lower sum and upper sum, when I speak. Lower sum, I again got confused. Lower sum and lower integral, and upper sum and upper integral. So here is the proof. Let tau be a subdivision of a comma b. Then we have little s sigma is at most capital S tau for all subdivisions sigma. This is what we just proved, which implies that supremum of this lower sum is at most S tau. Why? Because this was true for each sigma, so we can replace the left hand side by its supremum, and we still have this inequality, but the left hand side is the lower integral. So we have that, but now since this is true for each tau is arbitrary, so this is true for each tau, and therefore we can also take infimum on the right hand side for all subdivisions, which implies that the lower integral is at most the upper integral. And that's what we wanted to show. So yeah, we have seen at least some non-trivial things in this lecture, although everything is very, very easy. Okay, alright. So as usual, like, comment, share, subscribe. I also have Patreon. Listening, and I'll see you next time.